Welcome to ES 310 Lesson 34. Today we will learn how to solve three-dimensional kinetic problems using work energy and impulse momentum. This work will be based on the 3D kinematic problems we've been doing in the past couple of lessons. For more information about this topic, you can see Hibbler's Dynamics textbook, Chapter 21, Sections 1 through 3. The primary difference or addition that occurs because we're in 3 dimensions for work energy and impulse momentum type problems is the fact that now that we have an omega or an angular velocity that can be in directions other than the k direction, the k-hat direction, we need to worry about moments of inertias along different axes. So in the general case, we have a moment of inertia tensor, which includes moments of inertia in the around the x-axis, y-axis, z-axis, and products of inertia around the xy, xz, and yz axes. In special cases where the axes we're using are along the principal axes, we have principal moments of inertia. Typical the principal axis is a case where two axes are along the axes of symmetry for the body that we're working on. So if we have that situation where we're along the symmetric axes, we can reduce this to a diagonal tensor that involves Ixx, Iyy, and Izz. And so all of the products of inertia are equal to 0. For the generalized case, we can also write the parallel axis theorem, which now has some extra terms because we're dealing with 3 dimensions. So in the x direction, we have the x direction for the center of mass plus the mass times the y direction squared plus the z direction squared. Similarly, for the y direction, we have the y around the center of mass plus the mass times the x direction squared plus the z direction squared, and so forth. The products of inertia also have a parallel axis theorem, which is the axes we're interested in around the center of mass plus the mass times the distance to the center of mass in those 2 directions, x and y. For y and z, it'll be y and z. So using that tensor notation, then we can go back to the impulse momentum equations we've seen in 2 dimensions and simply expand them to 3 dimensions. So if you remember, for a momentum around an arbitrary point, so a point that is neither the center of gravity or center of mass of the object, nor a fixed point, so some arbitrary point A, the momentum is equal to the momentum around the center of gravity plus the moment of the linear momentum of the center of gravity. So the position of G as measured from A crossed with the mass times the velocity of the center of gravity of the object. This then can be written out in components. So the x direction is equal to the I moment of inertia times omega I minus the product of inertia xy times omega y minus the product of inertia xy times xz times omega z. Momentum in the y is equal to the negative product of inertia yx in the times x plus Iyy times omega y minus Iyz times omega z, and similarly in the z direction. This reduces, in the case of principal axes, to Ixx times omega x, Iyy times omega y, Izz times omega z, since all the products of inertia go to 0. So now that we found our momentum, we can apply the impulse momentum theorem using vector notation. So each of these equations represent 3 equations, right? So we have an x, a y, and a z equation from each of these. So we have 6 equations in our impulse momentum. If we're in a situation where there is no impulse and momentum is conserved, these integral terms simply go to 0, and we have conservation of momentum in the linear directions and conservation of momentum in all three rotational directions. We can do a similar thing for work energy. So, once again, using vector notation to generalize these for three dimensions, we have that the kinetic energy is 1/2 of omega dotted with the momentum h. The expression we're used to seeing is 1/2 of omega dotted with I omega. So the expression we're used to seeing is 1/2 I omega squared. We've got a dot product now, since we're dealing with three dimensions and omega can have more than a single component, but this is the same expression that we're used to seeing for rotational kinetic energy. Around the principal axis, then that reduces to 1/2 of Ix omega x squared plus 1/2 of Iy omega y squared plus 1/2 of Iz omega z squared, which is simply a dot product, right? The x component times the x component, the y component times the y, and the z times the z. Around the center of mass, we have to include the linear kinetic energy of the center of mass. So we have a 1/2 omega dotted with the momentum around O, that's the fixed point, plus 1/2 of the mass times the velocity of the center of mass squared. That is a single term, right? Because this is the magnitude of the velocity. And then we have the same three terms that we had around principal axes previously. Once again, now that we've found kinetic energy, we can use principle of work energy, so that the kinetic energy is equal plus the work is equal to the kinetic energy, or we can use conservation of energy that says T1 plus V1 is equal to T2 plus V2. The expressions for work and for potential energies don't change based on three dimensions. A spring is still a spring, creating either work or potential energy due to its stretch, and gravity still is acting in a single direction, the k direction, creating work or potential energy due to gravity. So let's take an example of this. This example is set up so that it is also a reminder of the kinematics type problems of collars on rods. This is a somewhat long example, but we'll go through the setup for it, and I'll skip over some of the details of the math, but I'm sure that you can fill that in. So what we have is a series of rods with collars. There's a spring attached to the collar at B, and collar at A is given initial velocity downwards of 8 feet per second. In the situation shown, the stretch in the spring is equal to 0. So let's write our expressions for kinetic and potential energy. The idea is if they're given information about this state, then we're asked about information about when the collar VA gets down to the point where Z is equal to 0. So the initial kinetic energy for our system will have a rotational component and a translational component. So the rotational component is 1/2 of omega dotted with h. We can also write this as 1/2 of IAB omega 1 squared. The linear part is going to be plus 1/2 of mass times the velocity of the center of mass squared. The potential energy initial, we're told that the spring is unstretched, so it has no potential energy. 1/2 ks squared is going to be 0 because s is 0. Plus the potential energy of gravity, so the center of mass is sitting halfway up the bar. If the whole bar goes from 0 to 3, then it is 0.1 or 1.5 above the datum, the 0 plane. So this is mgh, or z, which is going to be, mg is the weight. So 6 times 1.5 is the height, which gives us 9. Then we have an expression for T2, which is 1/2 of IAB omega 2 squared plus 1/2 of mvg squared. These are 2's. And we have potential energy 2, which, so in the state 2, this bar has come all the way down here, so we're purely in the xy plane. If we look at it from above, we've got a triangle that looks like this. That's the bar we're given. It's 7 feet long. This distance is 6, because that rod hasn't changed. And so we can figure out what this distance would be based on Pythagorean theorem. So this is, let's call it x because it's in the x direction. So we have 7 squared minus 6 squared is equal to x squared. So x is equal to 3.6. We can also from x figure out what the stretch in the spring is, because originally the spring is 2 feet long. So S is going to be 3.6 minus 2 is equal to 1.6. That's the stretch in the spring in our final situation. So the gravity has no potential energy because the center of gravity is now on the datum plane. But the spring has potential energy, so we have 1/2 k times 1.6 squared plus mgz, which is now 0. So we have basic expressions. If we look at them, we have this omega 1 in Vg. We know Va, but we do not know Vg or omega 1. They're related to Va, so we'll have to do some work to relate those. And similarly down here we have an omega 2 and a Vg2, and we're trying to figure out what is the speed at A. So here we're given the speed at A, we need to find omega 1 and Vg. Using that we're going to need to find omega 2 and Vg2, and using that we're going to find Va. So now we're down to the kinematics part of these problems, right? So we're going back to what we did in the previous chapter, in chapter 20, and looking at some kinematics. So we are given information about VA. We are going to use VB because we have information about the direction of VB. So we're limiting a few of the unknowns. So we're going to say that VA is equal to VB plus omega AB crossed with RA, so the position of A as measured from B. So if we write these out as our vector notation, VA is a speed of 8 going downwards, so we've got negative 8 k hat is equal to VB. We don't know what it is, but we do know that it's in the I hat direction. Right, because along this bar is the I hat direction, plus this cross product. We don't know anything about omega. I'm going to call it omega x, omega y, and omega z. We don't know anything about any of those components. The RAB we do know. So the position of A relative to B, to go from B to A, we need to go negative 2 in the x. And we need to go negative 6 in the y, and then we need to go up 3 in the z. So then we can do this cross product, take the I hat, j hat, and k hat parts, and the expressions we're going to get is for the I hat direction, we're going to get 0 is equal to VB plus 3 omega y plus 6 omega z. The j hat part is going to be 0 is equal to negative 2 omega z minus 3 omega x, and the k hat part is going to be 8 negative is equal to negative 6 omega x plus 2 omega y. This has 4 unknowns but only 3 equations, so we need another equation. And that equation comes from the fact that they tell us that omega AB is perpendicular to the rod's direction RAB, which tells us that the dot product of these two, omega AB dotted with RAB, is equal to 0. And so that gives us the expression, we take the x part of omega times the x part of r, we get negative 2 omega x minus 6 omega y plus 3 omega z is equal to 0. Now we have 1, 2, 3, and 4 equations and 4 unknowns. So we can solve that then for all 4 of the unknowns. And those end up being VB is equal to 12, omega x is equal to 0.979, omega y is equal to negative 1.06, and omega z is equal to negative 1.47. So knowing that, we can now write omega 1 is equal to the square root of 0.979 squared plus 1.06 squared plus 1.47 squared, which is just the amplitude, so the sum of the squares square root, and this turns out to be 2.06, so that's the omega 1 up here. And our next task then is to find VG. Well, VG is yet another expression like this first one, right? Vector expression, which written out gives us that VG, the vector, is equal to VA, where we know the speed, plus omega AB crossed with RGA. We now know omega AB. We know RGA, which is just the halfway point of this on this bar, and we know VG, so we can solve for, or we know VA, so we can solve for VG. Writing this out, we get negative 8 plus this cross product, which is just these 3 numbers, omega x, y, and z, crossed into, so this is 0.979, negative 1.06, negative 1.47, crossed with our position of G as measured from A. So we're going to go positive halfway down is 3 in the Y, positive halfway through here is 1 in the X, and halfway down is 1.5. So X was 1, Y is 3, and Z is negative 1.5. We can take that, you can take that vector, those vector notations, and we discover that VG is a vector that has an I component of 6, a 0J component, and a Z component, or a K component of negative 4. So the magnitude is the square root of the squared. 6 squared plus 4 squared gives us 7.21. Alright, so we're going to move on to the next slide, and we're going to use, so this is our initials, so these are all 1s. So now we have we can find a number for T1, and we have a number for V1. We're going to use that to find the number for T2, given that we also have a number for V2 already. So that's what we're going to do on our next slide. We're going to plug in VG1 and omega, so this number and this number go into this top expression, and we get values. So what we're going to find is that T1 is equal to 6.46, V1 is equal to 9, V2 is equal to 5.12, which allows us to write T2 equal to, so T1 plus V1 is equal to T2 plus V2, so T2 is equal to T1 plus V1 minus V2, which gives us a value of 10.304. This is equal to, from before, 1/2 of I, which is 0.76087, times omega 2 squared plus 1/2 of the mass, 6 over 32.2, times VG2 squared. So we still have 2 unknowns in one expression. We need to figure out what's the relationship between omega and VG. So that, again, is going to be using the kinematics. So we're done with the energy for the moment, and so we're going to use kinematics. We're trying to relate omega 2 and Vg2. So we write out, once again, that Va is equal to Vb plus omega AB crossed with RAB. And we're now looking at situation 2. Right, so state 2. In state 2, this bar's come all the way down here, and this bar is stretched out, so what we have is the bar out here, and the spring is stretched out. So that's our situation, so that's our geometry. VA is what we're trying to find ultimately, so we don't know VA, but we do know that it's downwards in the Z direction, so K hat is equal to VB. We don't know VB, but we do know that it's in the I direction, right, because it's along this bar. It could be negative or positive. Most likely it's positive. So then we have a cross product plus I hat, J hat, K hat, and we don't know omega x2 or omega y2 or omega z2. We do know our direct distances, so R of A as measured from B is this line going in that direction. So we're going to go negative this distance in the I direction, and we figured out this distance of the previous slide to be 3.6. And we're going to go negative 6 feet in the J direction, and there's no distance in the K because we're on the same level. So our directions here, negative 3.6 I hat, negative 6, and 0. We can take this this cross product and add it in the VB, and we're going to end up with 3 expressions. The I hat expression gives us that 0 is equal to VB plus 6 omega Z2. The J hat direction is going to give us that 0 is equal to negative 3.6 omega Z2. And the K hat direction is going to give us that negative A, VA, is equal to negative 6 omega x2 plus 3.6 omega y2. So from this expression here, we get that omega z2 is equal to 0. Plug that in up above, and that means that VB is equal to 0. If VB is equal to 0, then point B, which is out here, is our instantaneous center of zero velocity. It's not moving, the velocity is 0, so it must be our IC. And we'll be able to use that then to find the velocity in the G direction. We can't solve these quite yet because we have 3 equations and 5 unknowns. So we can't relate the omegas currently. But we do have one more expression because, once again, omega AB needs to be perpendicular to RAB. So omega AB dotted with RAB is equal to 0. So we have our last equation, which says that negative 3.6 omega x2 is minus 6 omega y2 is equal to 0. So we can write this then as omega x2 is equal to negative 6 over 3.6 omega y2. Or that omega x2 is equal to negative 1.667 omega y2. And so we now have an expression that relates omega x2 to omega y2. We can plug that in up here and find an expression that relates omega y2 to VA. And so that is leading us towards being able to go up to our T equation and only have one unknown. Except in the T equation we have a velocity of G, not velocity of A. So we have to do kinematics again. We're going to have the expression that Vg is equal to, we're going to use Vb this time because Vb has a zero velocity, so things are going to be somewhat simpler. And that is equal to this cross product of omega AB crossed with R of G with respect to B. So this cross product then, we have the I hat, J hat, K hat. We have negative 1.667 omega y and omega y and 0. And then we have, if we're looking at R from G, which is sitting here, this is G2, right? So it's halfway in the x, halfway in the y, so this will be negative 3.6 over 2 and negative 6 over 2, 0. Take that cross product, we get k hat times 1.667 times 6 divided by 2 omega y plus 3.6 over 2 omega y. So now we've related Vg to omega y, and we can go back up to our kinetic energy expression and plug that in, that relationship in. The kinetic energy equation T2 is equal to 10.304 equals 1/2 of the 0.76087, which is our IAB, times omega 2 squared. Well, omega 2 is right, where's omega 2? We have omega 2z is 0, omega y is unknown, and omega x is written in terms of omega y. So if we add those two, add the squares and the square root, we get here 1.667 squared plus 1 squared times omega y squared. All right, so that's our first expression, the rotational kinetic energy, plus 1/2 of 6 divided by 32.2 times Vg2 squared. Well, Vg2 is the square of this, right, because there's only one direct component. So we get 1.667 times 6 over 2 plus 3.6 over 2, that number squared times omega y squared. The only unknown in this is omega y, so we can solve for omega y. Omega y is equal to either plus or minus 1.34. Our VA needs to be a positive number and for it to be going downwards. If we know omega, this is plus or minus, then VA is equal to, back up to this expression right here. We can write VA then is equal to 6 times negative 1.667 times omega y minus 3.6 omega y. And this needs to equal 18.2, and for that to work, this must be a negative 1.34. So that then is the answer to our problem. Notice the energy part of this was pretty straightforward, right? The conservation of energy was fairly straightforward. It was the kinematics from the previous chapter that was the involved part. But we just kept using this equation over and over again for different points and worked our way through it. In our second example, we're going to look at an example which has momentum involved. We are told we have a 5-pound circular disc and it's spinning, and then it's mounted on this L bar, which we're assuming is massless, and the whole thing is spinning. So we have, once again, a rotating coordinate system like we had in the previous chapters, and we know that our total omega is going to equal our omega 1 plus our omega 2. All right, so omega 1 is 15 radians per second around the axis that's parallel to the x-axis. So that will be 15 radians per second I hat. And we have omega 2, which is 6 radians per second around the z hat, so plus 6 k hat. So that's our omega. Now we're asked to find the angular momentum of this disk around point O. Alright, so let's start by finding the angular momentum around point B, and then we can translate, because the angular momentum about point O is equal to the angular momentum around the center of mass, plus R crossed with mv of that center of mass, which in this case is B. So let's start by finding HB then. HB is going to be, so first question is, do we have principal axes? And we do, right, because this axis and that axis and all three of those axes are axes of symmetry. All right, so we can use our principal axes, so that's going to be Ix omega x I hat plus Iy omega y j hat plus Iz omega z k hat. All right, so what is Iy, Ix, and Iz? Well, if we look at the reference table at the back of the book, we have that Ix is the one around the axis pointing perpendicular to the disk. So that will be 1/2 of mr squared, which is equal to 0.025. And Iy is equal to Iz, which is the axis in the plane of the circle. And those are 1/4 of mr squared, which is equal to 0.0125. So we have those numbers. And we have omega x, omega y, omega z from this expression. So we'll plug those in. So we get 0.025 times omega x, which is 15, plus there is no omega y, so this is 0, plus 0.0125 times 6, which is the k hat part. So this is I hat, this is k hat, and so that reduces to numerically 0.375 I hat plus 0.075 k hat. Alright, so now we're going to go back to this expression and apply that. So HO is equal to 0.375 I hat plus 0.0, that's a 7.5 k hat. Well, it's plus a cross product, so we'll set that up as an I hat, j hat, k hat. The R is from B as measured from O. So to get from O to B, that's our R, we're going to go 0 in the K, we're going to go 0.4 in the I, and we're going to go 0.3 in the J. Now our M times VB is our next question. I'm going to put the M out here because it's multiplying, and the question is, what is VB? So we need to do an aside for VB, and if this whole thing is rotating at 6 radians per second, then the speed of that point is going to be equal to omega 2, the 6, crossed with RBO, right? Because this is a stationary point, so this is our standard equation for using a stationary point. All right, so let's take this cross product, which is 6k hat crossed with 0.4 I hat plus 0.3 j hat. Well, k crossed into I gives us positive j, k crossed into j gives us negative I, and we get negative 1.8 I hat plus 2.4 j hat. That's our velocity in B, so that's what's going to go in over here, and M is our mass, which is multiplied by each of them. We've got negative 1.8, 2.40. We can take that cross product multiplying by 5, which is our mass, and we end up then with
3.75 doesn't change, right? Because if we do this cross product, the I part's going to be 0. The J part's going to be 0. All we'll have is a K part. All right, so this is I hat plus 0.075 from before, plus 5 times 0.4 times 2.4, 2.4, plus 5 times 0.3 times 1.8, and that is in the K hat direction. So our final answer for HO is 0.375 I hat plus 7.575 K hat. Then our kinetic energy is going to equal 1/2 of omega crossed with HO, or which then equals 22.5 joules.